So my name's Mapleson. I'm a scientific programmer in the sequence analysis and assembly group at the Genome Analysis Centre, which is based in Norwich, on the edge of Norwich. So it's this building here in the research park, which has got close affiliations with the John Innes Centre and the Sainsbury's Lab, and also a number of other institutes like the UEA and College Hospital. They're just off the picture. So at the Genome Analysis Centre, we get a lot of collaborators come to us and ask us to sequence and quite often assemble non-model organisms. And so we get the data in, the DNA in. The DNA, we have basically a bunch of DNA. We sequence it in our sequencing machines, and we end up with a number of reads, in this case paired sequencing, although there might be a number of other different types of sequencing that we've actually used. And my job is to assemble the data. So what we actually do is move from these reads and try and recreate the original DNA in the computer. So the common analogy that has been associated with de novo genome assembly in this way is basically the equivalent of trying to put together a multi-million piece jigsaw puzzle without actually knowing what the picture on the cover of the box is. So actually what we find with non-model organisms is it's a little bit more complicated than that. In practice, we actually don't just recreate the jigsaw once, we do it many times. We do it many times for a number of reasons. Basically, one of the problems with non-model organisms is that we haven't really developed a fit pipeline that works well in all cases. So we might want to use different assemblers, for example, manipulate the data in different ways. Also, our collaborators start asking us questions like, how do we actually know this assembly you're giving us is any good? What we actually need to do is to, because we don't have a reference to work with, we need to compare different assemblies, try and work out which one of our assemblies might be better than the others. The assemblers generally take in different parameters, and we don't necessarily know in chloride which particular parameter setting would work well in all cases. So this is really just going on, talking about what was in the last slide, but specifically the things that we will need to vary during our assemblies is our choice of assembler. So sometimes if we have all of the right sequencing data, we might choose to use all paths, or if we don't have all of that, there might be other assemblers that we prefer to use. We don't necessarily know which one will work well all the time. We also have the k-mer length. I'm not going to go into detail about what k-mers are. I'm sure a lot of you are quite familiar with them. But depending on the read lengths of your sequences coming in and factors in the actual genome itself, you might want to use different k values. Also, potentially you might want to pre-process the data. So often what we find is actually putting in raw data works fine, but sometimes you might want to consider actually quality trimming the reads or error correcting the reads. And also found assemblers can be quite sensitive to the level of coverage of the data that you actually pass in. So we're in a lucky position where we actually sometimes have plenty of coverage on our data, particularly for the smaller genomes. And in those cases, it might not be the case that we can always, the assemblers might not assemble well if we pass in all the data in one time. So sometimes going for a level around 50x coverage or maybe slightly higher actually works best, but there's not always one particular value that works well. And then also afterwards, after we've created the assembly, there might be other post-processing options that we need to look at. So scaffolding those in, potentially deduplicating content within the assembly. So as I mentioned, we can do all of this. We can try out all of those different options. But obviously, we end up with a lot of different assemblies then. So then we need to ask the question: how do we work out which assembly is best? So you can basically look at whether the assembly matches our expectations. So you can look at things like known genome length. If our assembly is coming out like that, maybe that's a good sign that it's an okay assembly. We can look at the contiguousness of the assembly and 50 values, but the trouble with this is that it ends up rewarding the more aggressive assemblers, and basically potentially creating the noise assemblers. And then there's other things we can do, like looking at alignments, so mapping reads to the assembly, seeing how many map back, and possibly if we have a reference that's not too dissimilar, we can try and map in context from our assembly to that reference. And actually inside TGAC at the moment we're looking at various behavior analysis approaches which actually can do a pretty decent job of comparing assemblies and working out whether we're using all the content from our reads in the assembly, how much distinct content we have in the assembly and that kind of thing. But that's for another talk. So we have these problems, and so I was asked to start assembling these things for assembling different genes for our collaborators, and I ended up finding myself writing a lot of scripts. And in the end, I thought this is getting quite difficult to maintain the scripts, so we developed a Java-based configurable pipeline for managing all of the issues that we had beforehand. So RAMPART is a configurable pipeline for generating and comparing multiple to no genome assemblies. And the idea of this was to reduce the bioinformatician's workload, or my workload in this case, to increase consistency and reduce errors. We also, while putting together the pipeline, would find that it would be nice to have a single interface for basically accessing multiple samples as well. Also, two other slightly different points is that at TGAC we have quite a big array of high-performance computing resources. So we have cluster and a number of shared memory, and we'd like to be able to move this pipeline across our different resources. Like scheduling systems like LSF and PDS, so we'd like to be able to manage both of those as well. And a knock-on effect from that is that we're actually, by doing this, we're actually thinking about the portability of the software. So we'd like to make it patched up in a way that can be ported to other environments and used outside of the Genome Analysis Centre. The pipeline that we've got is a very simplified version of the pipeline. We take in a configuration file describing the job, so the reads that we have available, and descriptions of exactly what tools we want to use and how much parallelism to use at various stages along the way. We also have an environment configuration as well, which will describe which scheduling system you're using, whether you want to use a scheduling system or not, which key to use, and that kind of thing. And that should be set up once you've got quite a bit of an environment. Basically we go through a number of steps, and now at the end we have potentially a single optimized assembly. If you want to trust the decisions that the tool is making. Otherwise, we'll have all of the various assemblies that have been produced along the way, along with graphs, tables, and logs that have been produced in that process. So the various steps we've got, a tool called MEC, which stands for Multiple Error Correction and Quality Trimming Tool. So this will produce various different data sets to be processed. The next step is MAS, which stands for Multiple Assembly Tool. That will take all the different data sets and assemble them with different K-MEA settings. After this stage, you end up with a lot of different assemblies. So there needs to be a decision made about which one is the one that you want to take forward. After that, we have another step called AMP, which stands for Assembly Improver. And that step is involved in basically adding any extra scaffolding or gap closing tools for us to try and improve the assembly further. And I've also been asked what RAMPART stands for before. So it's actually had a various number of different names, and it's slightly contrived, but the name we've got at the moment is the Fast Automatic Mean Parallel Assembly Toolkit. So we'll talk briefly about the architecture. So we've just looked at the pipeline, which actually is a single jar at the top, which actually encapsulates two other different Java projects underneath. At the bottom, we have a project called Conan, which is actually made by the EBI, and that, like a number of other projects that we've heard about today, is a workflow management application. Their actual words are extremely lightweight workflow management application, and the reason we decided to use this was that, first of all, it was written in Java. Second of all, it was really lightweight, and by incorporating that into our pipeline and our project structure, we can basically just create a single jar that can be moved around anywhere, and that is the whole of the project. The other aspects, there are a couple of other points that I should mention about Conan. That's that we're actually collaborating with the EBI on this project at the moment to extend it and to make Conan work in different environments a bit more, because it was quite LSF-centric to begin with. So what I've actually been working on is creating this concept of execution context, so that you can describe which type of scheduler that you actually want to use. So the idea is you can take an external tool, put it wrapped up as a Conan process, and then execute it in different ways. So the external tool API is basically a project which will actually take external tools, such as our assemblers, basically do mappings between Java objects and the arguments that would actually be passed in and deal with the output from that. So in this way we can actually keep all this code separate from the underlying Conan project and our pipeline. So we can reuse this for different pipelines that we might use for different projects in the future. Also, one thing that we've found that it can be quite a problem when trying to chain together tools in a script is that you end up with some external programs that need a configuration file as input, and so that has to be generated manually into that tool. So this project can actually handle that kind of issue. So this is quite a dry slide with just the current set of tools that we have in our in the pipeline. The features that we have are so we support LSF scheduling. We have PBS almost implemented, but it's not quite tested yet, so that might not work in my area on that. But it should be fixed fairly soon. So in terms of parameterized optimization, we can deal with different gamer values, we can deal with different pre-processing options, and we can also auto-step-based assembly. And what we really want to do, as I mentioned before, was to create this as a framework where we could actually test different assemblies as well, and make it environment agnostic. So moving on to the future, what we'd like to do is incorporate DRMAA and create an instance, implement this API and use that as a way of being able to run our pipeline in different scheduling systems. So at the moment we're although it's fairly scheduling system agnostic, we still need to write a lot of the code for different scheduling systems, and this hopefully will give us a way of doing that in an easy way. Also, as I mentioned before, we have inside TPEC various gamer-based analyses that we can do on the assemblies, and we'd like to incorporate feature response curves as well. I won't go into details at the moment, but you can come talk to me later if you want to know some details about that. Also, we can actually identify some contaminants that might be in the assembly as well, so we can see contigs that may not actually belong to the original organism that we're trying to assemble. So we would like to incorporate this as well. And as I mentioned earlier, coverage we might try to incorporate a different coverage optimization step. In terms of availability, it's all open source, it's on GitHub, we're using Java and Maven. The RAMPART projects, the actual pipeline here is available under the GPL version 3, as well as the wrapped processes underneath. The Conan 2 is actually available from EDI. If you want to actually make use of it and start editing the code and working with us on this, then please use the code of the Conan Next branch. That's what the levels bar are actually dependent on. But we have a current stable version tagged in GitHub. It also has a recompiled shading chart that's available there. So to summarise, just to clarify, I've been asked this a few times, I'm not making a new assembler. The assemblers are good at what they do, and we want to keep making use of those. So this is a computable and portable end-to-end engineering analysis pipeline that can cater for parameter optimization, and also can compare different assemblies and potentially validate those assemblies as well. And we are using this inside TGAT on a number of different projects at the moment. And the website is currently work in progress. So, but we do have that stable version available. So I'd just like to thank the people inside TGAT that have been working with me on this, and to Tony Burdett from EDI who developed Conan originally. So yeah, thanks to everyone for listening. Any questions?